Hello dear friends, welcome back to the series of lessons on heat transfer. This is Rama Krishna from Yale University. Today's topic is heat transfer through composite cylinders. This is under one-dimensional steady-state heat conduction without internal heat generation. So far we have seen the heat transfer through a slab, through a hollow cylinder, and through a hollow sphere. And we have also seen the heat transfer through a composite slab. We have defined the thermal contact resistance that occurs between the two layers. And today we will see the heat transfer through composite cylinders. At the end of the session, you will be able to understand what is a composite cylinder and how to evaluate the resistance of each layer offered for conduction heat transfer in a composite cylinder, and how to consider the electrical network to solve the conduction heat transfer problem for a composite cylinder, and how to evaluate the heat transfer through this cylinder, and more importantly, what is the effect of interchanging the insulating layers on a cylindrical pipe, and how to consider equivalent electrical network when there is convection combined with conduction, and what is a overall heat transfer coefficient, and what is the significance of it, how to evaluate it, and finally, what is critical radius of insulation and what is the importance of critical radius in different engineering applications, and how to estimate the critical radius of insulation for a cylinder. So let us start with a multi-layer cylindrical application. Most of the times, either in a process industry or in a power plant, the pipes carrying hot fluids are insulated. Sometimes with one layer of insulation and sometimes with two layers of insulation. So imagine there is a pipe which is covered with two layers of insulation, each layer having thermal conductivity K1 and K2. When we cover the pipe with layers of insulation, and these insulating layers are also called as laggings. So when you provide lagging on the surface of a cylinder, what happens to the rate of heat transfer from the cylinder to the surroundings or from surroundings into the fluid? How to estimate it? That is what we are going to see. So now this pipe of radius R1 is covered with first layer of insulation having thermal conductivity K1 and another layer of thermal conductivity K2. So because of adding insulation on the pipe, the radius of the pipe is increased to R2. So the thickness of the pipe is, the thickness of the insulation is R2 minus R1. Now imagine one more layer of insulation is applied on the pipe, again increasing the outer surface area of the pipe to R3. And the thickness of the second layer of insulation is R3 minus R2. Let the temperature at the surface of the pipe is T1, at the interface is T2, and at the surface, outer surface is at T3. So for the heat flow from T1 to T3, there are two resistances. And those two resistances are the conduction resistances offered by insulation 1 and insulation 2. For the heat flow from the pipe to the environment, these two resistances act one after the other. First heat has to flow through the layer 1 and then it will flow through the layer 2. So the resistances are acting in series. Resistance of insulation 1, say R1. Resistance of insulation 2 is say R2. Before this, the temperature nodal point here is T1, and at the end of the second resistance, the temperature is T3, and at the interface, it is T2. Heat flowing through each resistance is say Q. Now, this resistance is the resistance offered in radial direction for the heat transfer in a cylindrical system. Hence, as we have seen earlier, the cylinder conduction resistance formula is 1 by 2 pi KL log R2 by R1. Hence, the conduction resistance offered by the first layer is 1 by 2 pi K1L into log R2 by R1. Similarly, the second layer is from R2 to R3. Hence, the conduction resistance offered by the second layer is 1 by 2 pi K2L logarithm of outer radii by inner radii R3 by R2. So totally there are two resistances. Resistance offered by insulation 1 and resistance offered by insulation 2. So hence Q equal to T1 minus T3 divided by the total resistance between these two, R1 plus R2. So which is equal to 1 by 2 pi L comes to the numerator as a common term. So 2 pi L into T1 minus T3 divided by 1 by K1 log R2 by R1 plus 1 by K2 log R3 by R2. This is the formula to determine the total heat transfer from inside surface to the outer surface, passing through the two conduction resistances of the layers R1 and R2. A problem. Imagine there is a steam carrying pipe having thermal conductivity 45 parts per meter Kelvin of 75 inside diameter. So radius is 37.5 mm R1 and 90 mm outside diameter. So R2 is 45 mm. Is ranked with two layers of insulation. The layer in contact with the pipe is 38 mm thickness asbestos. So R3 is R2 plus 38 mm. That is 45 plus 38. You can see here 83 mm. And then 25 mm thick magnesium insulation. So R4 is R3 plus 25. That is 83 plus 25, 108 mm. The inside surface temperature of the pipe is 300. The outside surface temperature is 40. If the length of the pipe is 60 meters, calculate the heat transfer and the interface temperatures. Let us say the first inside surface temperature is T1 and outer surface temperature is T4, 340. If you carefully look at this problem, for the heat to flow, first it has to flow through the pipe wall. And this pipe wall offers conduction resistance. Then after crossing this pipe wall, it has to pass through the insulating layer 1, that is asbestos. And then again it has to pass through the magnesium. And then it reaches the surface. So from inside surface of the pipe to the outer surface of this second insulation, there are three resistances. First one is conduction resistance offered by this pipe. The second one is conduction resistance offered by asbestos. Third one is conduction resistance offered by magnesium. And I can see that all the three resistances act one after the other in series. So let the temperature at the interface is T2 here and T3 here. So from T1 to T4, you have in between here T2 and here T3. T1 is known 300, T4 is 40. So between the two nodes known temperatures 300 and 40, there are three resistances. Therefore you can write Q equal to delta T, T1 minus T4 by the total resistance R1 plus R2 plus R3, R pipe, R asbestos plus R magnesium. And all these are cylindrical resistances. For conduction, the formula is 1 by 2 pi KL log R2 by R1. So the pipe resistance is 1 by 2 pi K1L log R2 by R1. Next insulation resistance is 1 by 2 pi KL K2L log R3 by R2. Next, third outermost insulation resistance is 1 by 2 pi K3L log R4 by R3. So let us calculate pipe resistance. You know R2 and R1. We know K1 value, pipe 45, and this is the pipe resistance in degrees centigrade per watt. Similarly, asbestos in degrees centigrade per watt. Similarly, magnesium in degrees centigrade per watt. Add these three, you will get total resistance, which is equal to 0.0216 degrees centigrade per watt. That is how these three resistances are acting. So Q equal to 300 minus 40 by R total you will get 12,038 watts is the heat loss from the inner surface of the pipe to the environment because of these three resistances acting one after the other. Now, if you want to find these interface temperatures, according to law of conservation of energy, the heat flowing through the first resistance, second resistance, and third resistance is same. So let us tap these two nodes, T1 and T2. So Q through this resistance is T1 minus T2 by pipe resistance alone. So the unknown in this is T2. You can determine T2. And similarly here, Q is equal to T2 minus T3 by R asbestos. Now the unknown is T3. You can determine the value of T3. Over, you got T2 and T3 values. You can also do like this. Q is also equal to T3 minus 40 by R magnesium. You can determine T3. Q is also equal to T2 minus 40 by T2 minus 40 by, between T2 and 40 how many resistance are there? 2. Therefore, T2 minus 40 by R asbestos plus R magnesium. So that is the advantage of having electrical analogy. Once you are able to draw this electrical circuit, you can determine the temperatures at any point and you can play with it. Another important conceptual problem. Imagine there is a steam carrying pipe having outside diameter 3 centimeters. So radius is 1.5 centimeters. Be careful, most of the problems related to cylinders, they give you diameters. But in the equations, when you want to find the outer radius after addition of the insulation, the thickness of the insulation only will be given. So you have to add the thickness to the radius, not to the diameter. Many students do mistake here by taking directly, adding directly the thickness to the diameter, and the problem goes wrong. So a caution is very important here. So when the steam carrying pipe is insulated with 2 layers of insulation, each of thickness 2.5 centimeters, say, look at this 1 and 2, insulation 1 and insulation 2, such that the average thermal conductivity of one material is 5 times that of the other. Say K1 is 1 and K2, and that K2 is given 5 times that of K1. Assuming that the inner and outer surface temperatures of composite insulation are fixed, that means the temperature at the end of R1, that is a Ts, and T alpha are fixed. Find the best arrangement of insulating layers that results in least heat loss. Very interesting question. That means if I keep insulation 1 and then immediately after that insulation 2, what is the heat transfer? If I interchange the layers like this, first I will keep insulation 2 and then I will keep insulation 1. What will be the rate of heat transfer? This is what you are supposed to do. Both insulations are having a thickness of 2.5 only, but thermal conductivity differs. K2 is 5 times K1. So to start with, let us assume insulation 1 is kept immediately after the pipe as shown in this figure, and next insulation 2 is kept. Now two resistances are there in series between Ts and T alpha. Look at this arrow. Between Ts and T alpha, you have two resistances, and these two resistances act one after the other, and they are in series. So Q is equal to delta T by 1 by 2 pi thermal conductivity of first layer K1 L log R2 by R1 plus 1 by 2 pi thermal conductivity of the second layer K2 L log R2 by R3 by R2. Log R3 by R2, a small correction is required. This is R3 by R2. That is, you can take out common 2 pi K1L, and K2 is 5 times K1. If you substitute that, when you take K1 common, the 5 remains here. So it is log R2 by R1 plus 1 by 5 times log R3 by R2. R1, R2, R3 values, as per the description of the problem, goes like this. Now arrangement 2. See, now the second insulation is kept first, and then insulation 1 is kept at the end. Again the same equation, Q equal delta T by R total. In the second arrangement, Q suffix 2 delta T by 1 by 2 pi K2, because first you have the layer with the K2 thermal conductivity, L log R2 by R1, no change in R2 R1 because thickness is same, plus 1 by 2 pi, next conductivity is K1 L log R3 by R2. So therefore, the heat transfer in the second arrangement is delta T by, again let us take 1 by 2 pi K1 L common. In the place of K2, we substitute 5 times K1. So when K1 goes off, 5 remains here. So 1 by 5 log R2 by R1 plus log R3 by R2. Now to identify which one will give the best heat transfer, you divide Q1 and Q2. So 1 by 2 pi K1L delta T in both these equations, delta T 1 by 2 pi K1L is common, it cancels. You will get 1 by 5 log R2 by R1 plus log R3 by R2. Because this is in the denominator, it goes up, divided by log R2 by R1 plus 1 by 5 times log R3 by R2. This ratio is 0.632. So which indicates that Q2 is greater than Q1. Or in other words, if you want to minimize the heat transfer, Q1 is the best arrangement. What is Q1? Keeping material with low thermal conductivity immediately next to the pipe. That is the conclusion. So the first arrangement is the best arrangement and gives less heat loss. Therefore, in a radial system, it is always advisable to place a better insulating material having lower thermal conductivity immediately after the pipe to minimize the heat loss. Interchanging the layers or position of insulating layers in a slab is immaterial because there is no change in area of flow. See, this situation occurs only for cylindrical systems because as you go on adding layers, the area goes on changes. But whereas in slabs, if you take whether the layer is initially or afterwards, that L1 by K1 A1, L2 by K2 A2, they interchange. The sum remains same because there is no change in area. So hence, in a cylindrical system, when you are going for a multi-layer lagging to reduce the heat loss from that cylindrical system, it is always advisable to have a better insulator immediately next to the pipe. Very important inference drawn through this example problem. Next. Convective resistance also exists when these type of cylinders are exposed to the environment. We have seen in the beginning the formula for convective resistance is 1 by HA, where H is the convective transfer coefficient representing the ability of the fluid to deal with the heat. So when H0 outside heat transfer coefficient, Hi inside heat transfer coefficient, when these are specified, it is must and should you have to consider the convective resistance also in addition to the conduction resistances. Unless this H0 tends to infinity, the T alpha 2 and the surface temperature will never be equal. Unless this Hi tends to infinity, the T alpha 1 and the inner surface temperature will never be equal. So due to the finite values of convective heat transfer coefficient, always there exists a temperature gradient between the surrounding fluid and surface, and that resistance is known as convective resistance. So as per the formula, convective resistance is 1 by HA, where A is the surface area to be considered. Now the formula, if you look at this equation, the temperature at the inner face is the T alpha 1 and outside is the T alpha 2. First you have convective resistance and then conduction resistance of insulation 1 and then conduction resistance of insulation 2 and then conduction resistance of insulation 3 and finally the convective resistance of insulation 4. So between T1 and T4 there are totally 5 resistances. Hence Q is equal to the temperature difference as a whole from T alpha 1 to T alpha 2 divided by R total. So Q equal to T alpha 1 minus T alpha 2 by R total, where R total is equal to convective resistance plus conduction resistance of layer 1 plus conduction resistance of layer 2 plus conduction resistance of layer 3 plus outside convective resistance. AI and A0 represent the inside and outside surface areas, where AI is equal to 2 pi R1L and A0 is equal to 2 pi R4L. So instead of considering only conduction resistance, by virtue of the phases exposed to a medium having limited convective ability, we are considering two more resistances called convective resistances, both inside and outside. So the total resistance is inside resistance due to convection plus multiple conduction layers plus the convective resistance at the outside. If you carefully observe, this involves logarithm and then reciprocals, etc. Calculation of R total is generally a tedious thing. So carefully we have to work out for this R total. Otherwise, most of the times, due to these reciprocals and logarithm and again reciprocals, etc., we may go wrong in calculation and we will end up with a wrong value. So thorough practice is required, or experienced people only can calculate this resistance when more number of conduction as well as convective resistances are involved in it. So that is the reason why they introduce one more coefficient called overall heat transfer coefficient. If it is pure conduction, you have conductance only. If it is pure convection, you have heat transfer coefficient. But whereas a problem like this, the resistance is offered both in terms of convective resistance as well as conduction resistance. So the total resistance is a combination of convection and conduction. So in such cases where you have combined effect of conduction and convection, we represent a new term called overall heat transfer coefficient. Hence, overall heat transfer coefficient is a combination of the effects of conduction and convection. So for convective heat transfer alone we use H, and for combined conduction and convection we use a coefficient U, overall heat transfer coefficient. The equation for it is Q equal to UA del. Very simple, remember, don't confuse. If I write Q equal to HA delta T, it is only by means of convection, and H represents convective heat transfer coefficient. If I use the formula Q equal to UA delta T, the U represent a combined or a overall effect of combined conduction and convection known as overall heat transfer coefficient. So Q is equal to UA delta T. But anyhow, while considering this area, which area I have to take? Is it inside area of this pipe or outside area including all insulation? If you consider outside surface area, then the equation Q can be written as U0 A0 delta T. If you consider it as inside area, the Q is UI AI delta T. So we have two equations. One is Q equal to delta T by R total. Q equal to delta T by R total. And the same Q is equal to U naught A naught delta T. So equate both of them. Q equal to U naught A naught delta T equal to delta T by R total. And that R total is first inside convective resistance, conduction resistances one after the other, and outside convective resistance. So if you compare delta T gets cancelled, and 1 by U naught A naught, bring it to this side and take this to the other side, is equal to 1 by HIAI plus 1 by 2 pi K1L log R2 by R1 plus 1 by 2 pi K2L log R3 by R2 plus etc. to 1 by H naught A naught. So this equation is very much useful to determine the overall heat transfer coefficient in a multi-layered system. Let us take a problem. A cast iron pipe thermal conductivity is given. Inside diameter 5 centimeters, outside diameter 5.5. Carrying steam at 320 with a convective transfer coefficient of 60 watts per meter square Kelvin. And this pipe is covered with an insulation having thermal conductivity 0.05 in a convective environment of 18 watts per meter square Kelvin, and the outer surface temperature of this is, the surroundings is at 20 degrees, and the inside fluid temperature is at 320 degrees centigrade. You are asked to calculate the rate of heat loss per meter length and the interface temperatures and overall heat transfer coefficient based on outside surface area. So first resistance offered is convective resistance, given by the formula 1 by HIAI. We know HI, and in convective resistance area is surface area 2 pi R1L. And the second resistance offered is conduction resistance of the pipe wall. So 1 by 2 pi K1L log R2 by R1. By substituting you will get this. And then the next layer is insulation layer, which is 1 by 2 pi K2L log R3 by R2. So by substituting the values you will get this. And the convection resistance outside is 1 by H naught A naught, 1 by 18, A naught is 2 pi R4 into L. So once you know all the resistances, you can calculate the sum of all the resistances R total equal to 2.61 degrees centigrade per watt. Now Q equal to delta T, that is 320 minus 20 divided by all the four resistances together react 2.61 as we have got here, and hence Q is 114.94 watts per meter length. And I think per meter length only it is asked. And now to determine the interface temperature, say this is T1, this is T2, and this is T3. You apply the electrical analogy again. Heat flowing through the entire circuit is Q. So through the first resistance also Q. So Q equal to 320 minus T1 by R convection. And the same Q equal to T1 minus T2 by R conduction 1. and the same Q equal to T2 minus T3 by arc conduction of the insulation, and the same Q is equal to T3 minus 20 by convective resistance. So you can use any equation to determine the nodal temperatures. So thereby you will get the temperatures at the nodal points T1, T2 and T3 as 307, 307.7 and 37.66. One important thing here you can observe through the solution. The temperature T1 is 307.8 and T2 is 307.77. That is, see here, T1 and T2. This material is cast iron exhibiting high thermal conductivity 80 watts per meter Kelvin. Because the conductivity is high and the thickness of the pipe wall, see here, the thickness of the pipe wall is hardly 0.25 centimeters, 2.5 mm. Diametral difference is 0.5, radial difference, thickness becomes half of it, 0.25. So within the 2.5 mm, for material having high thermal conductivity like steel with 80 watts per meter Kelvin or cast iron, the temperature drop is very, very less. So as the thickness is less, thermal conductivity is high, it offers very low amount of resistance for heat transfer, hence the temperature gradient is almost zero. So that is the reason why you get the same temperatures almost at T1 and T2. That is sometimes he may ask you to neglect this resistance also by giving directly the outer surface temperature of the pipe. Now because the insulation is having very poor thermal conductivity, it offers more resistance. You can now see a drop in temperature from T2 to T3, 307 to 37, very large drop because of its poor conductivity. And other equation to determine this Q is UA delta T. So by using Q is equal to U naught A naught delta T, you can also calculate U naught value, Q by A naught into T naught, that is 1.06 watt per meter square Kelvin. You can also find the overall heat transfer coefficient U by using the formula U naught equal to, or 1 by U naught equal to 1 by R total into A naught, or U naught is A naught into R total. You can determine this U naught. Now this problem in another direction illustrates how difficult it is to calculate the R total, this one. And then how difficult it is to calculate Q value. Suppose in an industry, if you are asked to determine the rate of heat transfer from the inside pipe to outside environment, which is covered with layers of insulation like this. Imagine you are given the U naught value, then your job is simple. You use the formula Q equal to U naught A naught delta T. This delta T is inside fluid temperature, which you can measure with the help of a thermometer, and this is outside surrounding temperature. And A naught, take a tape, put it around the pipe, you will get the outer circumference, from which you can calculate outer surface area per meter length into U naught A naught delta T. You will get the value of Q. Very simple. So a tedious problem can be simplified and reduced into a simple one, provided you are given the value of U naught, overall heat transfer coefficient. So as an engineer, it is our responsibility to give the value of U naught to avoid such tedious calculations in power plants or process industries. That is the reason why we have defined a overall heat transfer coefficient, and that overall heat transfer coefficient is equated to the same Q value, through which I got 1 by U naught A naught equal to so and so, and then that leads to the value of U naught. I hope you have understood the concept of giving U naught value. With the given U naught value, calculating heat transfer rate from a composite cylinder becomes much more simpler, and the amount U naught is specified whenever there is a combined conduction and convection.